Hello, good afternoon. Welcome to the last talk of a long conference. Thanks for coming. This is about transitioning from a batch processing system to a streaming pipeline. It's a use case. It's two parts to this talk. The first is the actual use case where this was applied, and the second part is how you could build something similar using the things that are available with Apache Apex, which is a stream processing platform. So it has ETL in the title, and as you probably know, many things can be understood under that umbrella. So ETL can be very simple, like having records processed one by one, do some filtering, discard some records, maybe do some map transformations and store them somewhere. But the kind of things that you would build with Apache Apex would be more complex, typically. Would probably involve windowing, aggregations, and things like that. And that's the kind of T that I want to talk about here. And then the L is in parentheses because in this case, we actually don't load the data anywhere, but we will consume the data directly from the streaming application for real-time reporting and visualization. So a little bit about Apex before we dive into the functionality that was implemented. Apex is a stream processing platform and framework, and it fits into the larger picture as you see here in the blue box. So you have many different data sources that continuously produce data. Mobile devices, logs, sensor data, you name it. And now we want to deliver that data for processing. So Kafka is the most prominent system in that space for streaming data. It can transport the data, it can store the data, and it's scalable, so widely adopted. Everybody knows Kafka. There are other messaging systems that can perform similar functionality. Once we have the data, then we can look at the processing part, right? And Apex you would use for the transform and to produce the data for analytics. And the way this is done is describing application logic as directed acyclic graph. And that can be, so the units that are being put into that graph are called operators in Apex. And they are connected with streams. And you can form simple sequences of operators. You can also have branches and joins, and that is enough to pretty much express any complex processing logic that you need for a streaming transformation. There are API to do that. There's a lower level DAG API where you pretty much put that graph together yourself. Compositional API, it's sometimes also called. There's a declarative API, higher level, that abstracts some of those things and make it look more simple or declarative or fluent style API. If you know Spark, for example, it has that style of API. There's also a support for SQL, some limited support at this time. And then there is an operator library that contains a lot of the building blocks that you need for pipelines. So as an application developer, you would normally start using the connectors and the transformations that are available in the library and build the application. And then most likely in any pipeline, there would be some custom code or some customization to existing operators, and that's the development work that would go on top of it. So connectors are there to tap into the data that are provided by the sources. So for example, there's a Kafka connector, or there is an input operator, as we call it, for RabbitMQ or for JMS and so on. And this is just a subset of the connectors that are available. And then likewise, there are connectors available to write to sinks, which often are files or databases. And sometimes when you think about a larger system that contains of multiple services or microservices, it could go into Kafka topic again for downstream processing. And what we will see in this specific case is actually that the data doesn't go into any of these systems, for downstream processing, but directly for visualization, for real-time visualization of the results. Apex needs a cluster to run, and at this time it runs on Yarn. In the roadmap is also to have support for Mesos, but the general idea is that you have a cluster, and then you can deploy an Apex application on top of it. So the use case, it's in online advertising domain, and it's the first of the 4 different things that are mentioned here. So real-time reporting, you have ad servers that produce logs, the logs, click logs and impression logs, and those things are collected, pushed to a hub through Kafka, and then aggregated and made available for reporting. So critical metrics around campaign monetization, utilizing revenue, impression, and click info. And there are other things that can be done with that data later too. After just making it available for reporting, it can be used, for example, to be fed back into the allocation engine for the bidding process. And we will talk about the first part in this session. So the state, when the project was started, this was implemented in 2014, by the way, so it's not brand new. But some of the concepts that were actually implemented, they are interesting today. So, and the general issue of having batch pipelines that just take too long to make results available is actually applicable across the board, not just in ad tech. So the issue was that time to insight was 5 hours, essentially, or more than 5 hours, due to how the data was ingested and processed. And that's a problem when you consider that decisions need to be made reasonably fast, let's say in minutes, to correct issues with campaigns and so on, to make better use of the money that's being spent. So the available data is stale. The current data is stuck in a batch pipeline. The pipeline itself was composed of many different technologies and pieces that were also hard to keep running and together. And yes, it took long. So the transition happened in 2 phases. The first one was to leave intact the ingest part, because the thing is with ad servers, the data ingestion is a critical part. The ad servers, they need to push the data to some sink, and they need to get rid of the data fast because their job is to serve ads, not to produce data for offline analytics. So initially, nothing was changed on the ingestion process. That means files were written, I believe it was every 15 minutes, into S3. And then downstream consumers could pick it up from there. Until they went to S3, of course, that also takes some time. That explains why it's not just 15 minutes, but 20 minutes. You need to wait, you need to batch up data, you need to run some job that takes it off. It really is a streaming. The ad server, when you think about it, is a stream, right, of logs. But to make it a batch, we have to wait, we have to collect that data, and then produce that 15-minute file that ends up in the file system. After 15 minutes, it becomes available to a downstream pipeline. The file is done or complete. It can be picked up by a reader, by a file reader. So this is what happened here in the first phase. The files were taken from S3. The downstream logic, the transformation logic was replaced, was done with Apex. So a file reader would transform the files back into a stream. That sounds kind of weird, right? Stream to file, file to stream, and then process it record by record, do aggregations, and produce the data that is suitable for reporting. What was implemented is was the dashboard, and so the entire processing logic was now on a stream processing platform with Apex. And then the final part that took a bit longer due to the sorting out the ingestion mechanism, where more dependencies are there, was to switch the consumer to go directly against Kafka and take the data from there, which then reduces the end-to-end latency to seconds. And I think something important to note here is that although it's very nice to have a low latency latency processing platform that can compute things as soon as they are, as soon as the input is there. It's actually the extract process or the ingestion process that determines the end-to-end latency. So 20 minutes was an improvement, right? Because you save 4.5 hours, but seconds is what was ultimately needed. So here was the first cut. You have the ad servers pushing through HTTP proxy the data into Kafka. The records get compressed, and there is also a micro-batching, 10 log records into one small batch, and then compressed because they have to go over the wire. This is geographically distributed. There are Kafka clusters in 6 different regions in the world, and then the data from those local Kafka clusters goes into the hub. And where you don't see any connection here, that was batch. It was Camus to take the data from Kafka, make files out of it, and the MapReduce job to bring files in the final format and put them into S3. So from S3, they would be picked up by the Apex pipeline, a file reader, and there's a little bit more. There is also decompress, of course, which is not shown here, then some filtering, and then the dimension aggregation that I'm going to say more later. The real-time dashboard is essentially powered by this piece. You have an operator that has the data, or a set of operators, logically one. You have a way to ask that operator questions. That's a query that comes in through Kafka topic, and the result being pushed back through a Kafka topic too. And this middleware box that you see here, that's a front-end server that serves the dashboard. So think of it as a UI widget. You open the dashboard, there's a UI widget. That UI widget shows specific data. And there's a key combination. And that query is sent to the backend. It goes into a Kafka topic. It goes into the running application because the application runs somewhere in the cluster. So the endpoint from UI perspective is the front-end server. And then the data comes back through Kafka as well. So this looks pretty complicated, right? But actually, it's a low latency solution, and it works very well. It's PubSub-based, and I think 100 milliseconds or so, you can expect the results to be back in the visualization layer. So phase 2, the only change is now the input, right? You see that Kafka, the S3 reader was replaced with Kafka input that directly gets data from there. And again, in the final picture, you see that all the data comes through Kafka, and the rest of the pipeline processing remains the same. So an Apex application can read from many different sources. It can be a real-time streaming source. It can be a file source. No matter what, the source will produce a stream for internal processing, and everything is processed record by record. This is how you can get very low latency processing, and we're talking about like you can get, depending on what functionality is and what application needs to do, 10 milliseconds or so is possible. So this is the end result, right? What you see. This is the dashboard of the customer. It's proprietary, and this is powered by that PubSub-based query mechanism. The data comes from the application. There are time series that are being computed, and there are top N lists being computed, and they can be shown here. When the user looks at it, they will see changes, the changes for the most current data point updating in real time, because we said multiple seconds end-to-end latency, which includes the data coming from the event generated by an ad appearing on a website, all the way to the data coming through the pipeline, through the aggregation, being reflected in an aggregate in a time bucket, and then visualized through the queryable state or query mechanism in the dashboard. Now, how does that computation work? So the source, Kafka or files, it doesn't really matter. It can be applied to historic data or to current data. Decompress, parse, that's a simple operation, record by record. Then enrich and map. Again, these are simple record-wise transformations. Then the dimensional compute. So what you see in green is producing the time series data and the top-end data. And it is split into two phases, really. The dimensional computation has a pre-aggregate phase. So all the data that arrives within a time interval here will be aggregated before it goes to the next operator. The reason for that is you will typically receive multiple events that can be pre-aggregated. And it is better to do that before pushing it to the next operator, because what needs to happen here is the data needs to be shuffled. This is a key-based storage, and it is partitioned. So every record needs to go to the right partition, and pre-aggregation can happen over here, then the shuffle, and then the operator that repeats the aggregation, basically performs the same operation again to compute the final aggregate and keeps the data in memory for access from the front end. When I say in memory, that's backed by checkpointing. So it doesn't mean that the data is gone when we shut down the system. It just means that it can be accessed from the memory for update, for write, and for read from the query. And to allow that, it needs to be checkpointed. When there is a failure, when it has to be recovered, the data needs to be saved in a durable state store or in a durable store, and that in this case is HDFS for the checkpointing. So the query mechanism, I already mentioned that front-end server sends a query over Kafka. It comes to the store. Then it is like a hash table lookup. So you have dimension keys like advertiser, publisher, and so on, location maybe. And the lookup occurs here against a hash table, logically, and the results are being pushed out and go back to the front end. So how does the table look like? You have dimension columns, and you have metric columns. And this is a simplified multiple facts, really, combined into one table, and that's why you see some empty cells here. And this is actually how it would look like in the in-memory representation. So in this example, we are aggregating by time, then by time or by hour, to be precise, then hour and advertiser, then hour and location, and then all three, hour, advertiser, location. And in the real system, of course, there are more aggregates and more combinations, and this is just an example. There are also minutes and days and so on. And incoming events look like that. Again, this is an example. If people come from the AdTech space, they will say, hey, this looks too simple, but this serves the purpose. So advertiser, we match then the keys that we find here against the yellow columns, right? And we repeat that as many times as we have combinations. So you have 4 different arrows here for 4 different combinations that we have to update. And then the metric fields, they are updated accordingly, just shown for the revenue column in this case. So with this, we prefabricate the data that are later needed for reporting. And later it will be just a matter of looking up in the table the data and giving it back to the front end versus running a complex query on a database to produce the data. So when you consider you wanted to store every single impression or every single click in a database, and then go to the database and pull the data out from there for reporting with a join and a group by potentially or whatever, that would be, well, probably very hard to impossible, at least not in a reasonable or cost-effective way. But it's not needed here, right? Because what the user really wants is aggregate data. They don't want to look at individual impressions. If we wanted that data, we would leave it in Kafka. Kafka is really great. You can keep a large amount of data in a sequential log, and if it's needed, we can process it from there. But what we want here is access, fast access to specific records. So scale, 6 geographically distributed data centers, and then all the different systems that they have. They produce, they have around 10 petabyte of data under management, and they take in 50 terabyte of data that comes from the auction and client logs per day. 40 billion ad impressions and 350 billion bits per day. And that maps to an approximate throughput rate of 450K events per second. The picture that I showed earlier here that actually has 64 instances of those parallel pipes that do the processing from Kafka, and 32 instances of the store operator that maintains the data by key in memory. So why was Apex a fit for that? Apex, this customer, before they implemented this, they evaluated multiple systems. They also looked at Storm. They also looked at Spark at that time. And why Apex was eventually chosen, or what is today Apex, is one of the reasons you can do state management. So I said that the store operators keep data in memory, right? And then we can serve it from there. That is only possible if the state is managed, because otherwise we can lose it potentially. So Apex can do that. You can have what is also called the continuous operator model. That you can keep data in the heap memory. There is a way to checkpoint it, and you can access it from there. And yeah, that makes also development easy versus having to write code. Okay, I have to write it to a database, I have to load it, and then all the complexities about consistency and recovery. So Apex can do exactly once results processing. It has the checkpointing, the support for windowing, and event time processing. It has also efficient recovery in the event of failures, and the queryable state pattern, which is something that is being talked about recently, and an advantage of stateful stream processors is something that could be done with Apex and not with the other platforms. So it's native streaming. With a native streaming engine, you can, provided that the operations allow it, that they are not blocking, you can get very low latency and high throughput and efficient resource utilization. It scales, so that was also a requirement. And then another requirement is that there are pre-built operators that can be used to develop the application versus having to write everything from scratch. And at that time, there were some connectors. Granted, many things have been built since then, and some of the things that were part of the solution, they have also later been made part of the Apex library. So you see some of those things here, connectors for messaging, file systems, NoSQL, RDBMS, some other connectors. And then most importantly, because that's the whole purpose of building the pipelines, is to do transformations. So there are parsers, filters, enrichment, and other element-wise or record, tuple by tuple operators, and then stateful operators like what we are talking about here, where you can do aggregations and windowing and have the data in memory. So how would you build something yourself with Apex, something similar? That's the second part of this presentation. And I picked Twitter as an example because it's a nice source that everyone understands. It's also real-time data. It's streaming. The thing that it is not, it's not a high throughput thing, really. Twitter is maybe 8,000 tweets per second. And from the Twitter developer API, you can get only 1% of that. Okay, I want to have something that I can run on my local machine, so that fits the purpose. Functionality in two branches. The one is to compute the top hashtags that we see over a window of 5 minutes. And the second branch is to compute some counters in 1 minute sliding window. The counters are simple. It's just the number of tweets that have hashtags, the number of tweets that have URLs in it. So it uses the queryable state pattern to visualize the results. And it will be seen in using Grafana dashboard, and then using for the PubSub exchange with the front end, it's using WebSockets instead of Kafka. But that really is just an example. You can use any messaging system, or you can use any other system that is suitable for PubSub. to do that. And the source code of the application, if you want to check it out yourself, you can do so later. These slides will be shared. So the end result will be this. It's also simple. This is Grafana, and Grafana makes it really easy to visualize data. It's JavaScript, it's open source, and it's easy to build an adapter that maps from the data that the Apex application produces, sends over the PubSub mechanism into the format that Grafana needs for visualization. So on the top, you see the top N with the hashtag and the counts. And then the last column you can ignore. This is just something that allows me to sort the table that has something to do with how Grafana works internally. And the lower one, and this is time series. Grafana was really made, I believe, for time series and for monitoring systems. And so this is just using time series for the counters. So how do we compute the hashtags? This is using window operator of the Apex library. And it contains of 2 steps. So the first step is a keyed operation, a keyed window. So the hashtag is the key, and the count is the value. And we are computing the count, and it's over 5 minutes. That's here. And it's using the in-memory storage. There's also another storage option that is HDFS-backed storage. This is called managed state. That allows you to really keep a large amount of data with overflow and efficient asynchronous writing and a write buffer and a read cache. The trigger is set to trigger at the watermark, which really is not part of this demo here. But what will bring us the updates is the firing at count-based firing. So whenever there's an update, the result panes will be emitted to the next operator. So after 25 updates, the updated value is emitted downstream. Downstream is a top N window. So why does it need to be a window? It needs to be a window because there needs to be some accumulation happening. So this here emits individual key value pairs. And this needs to collect the key value pairs from potentially multiple upstream partitions. And so top N is an operation that needs to see all the data before it can provide the result. So that's what this is doing. It will trigger the results on every change. And it's using, again, the in-memory storage because it's just a small demo and not much throughput too. So the key cardinality will be low. So how does the querying work? Here's a bit more detail. So we have the windowing operation, the top N. Then there's something called a snapshot server. That's really the thing that maps to the store operator that I showed you earlier. That's the guy that keeps the data that we can ask questions. And the questions are coming in through the PubSub. This is the orange line. And the results are going back into PubSub. This is the green arrow. And here on the right side, we have then the Grafana dashboard. This PubSub server is just simple. On one side, it's WebSocket. It's not just it's a gateway from WebSocket to HTTP. The data can be taken from WebSocket directly too, but it's much easier to deal with HTTP from a front-end perspective. You can look at these pieces too there in GitHub. So how does the queryable state work? So the snapshot server has the data, as I already said. It is told what the schema is. And that's here. So these are the fields that upstream operator has produced. In this case, hashtag count and that extra label field. And we configure the snapshot operator with that schema. And then we have another operator that is responsible to push the results to the transport that's chosen. In this case, it's WebSocket. It could be a Kafka operator. It could be something else too. So I have recorded a little bit of what is happening here. Although I'm not sure why this is showing only the last part. So something has not worked out with this demo. So I will describe it instead. So we have the application that runs, in this case on the laptop. It will read the tweets from Twitter. It will emit the results into the PubSub mechanism. The PubSub mechanism will keep always the last record that it receives for each topic. Okay, there we go. So this is the application. It's running in local mode. It's not running on the cluster. So it's not connected to the PubSub yet. That's why the exceptions. So it's necessary to start that server first. So after the server is running, the Apex application, or rather the WebSocket connector, will be successful pushing the messages there, and we see that the tweets are processed from the input. And then the next step would be to bring up the Grafana adapter that takes data from the PubSub. In this case, we first check using curl that the data is available for both for the top N and for the tweet stats topic, which is the same that the Grafana adapter will do. And that's just a simple node process. So it logs whatever it gets from PubSub. And then we can see in the UI how this is updating. As the computation occurs in the backend, we see the changes here happening for the top hashtags and also for the time series. So the application uses all things that are part of Apex that are part of the Apex library for the functionality. It's using a tweet sample input operator to consume the data from the Twitter API. It's using window operator to do the accumulations that I talked about for the counting for the top N and also for the counters, the tweet counters that you see in the bottom panel. It's using the snapshot server to handle the queryable state, and it's using the WebSocket output operators to push the data back into the PubSub. And of course, WebSocket input too, to get the queries from there. So what has changed in Apex over the last year? Apex has added a runner to Apache Beam. So it's one of the supported backends on which you can run Beam pipelines now. Support for iterative processing was added, which is something that you need for machine learning algorithms. And then an integration was built into Apache Samora based on that. There was also integration with Apache Calcite to enable SQL queries. Right now, the SQL doesn't support windowing, so it is just basically record by record transformations that make sense. Nevertheless, it's a first cut that can be extended. Then state management, which is really important when you want to build large applications with historic data and so on. Then you need the state management, so there are components available to do that, along with spillable, we call them spillable data structures, to make the use of such things easy, using Hadoop file system as backend. And then control tuples, user-defined control tuples that you can broadcast a control tuple, for example, for demarcation or other propagation purposes through the topology. So that was added as well. Then on the roadmap are to enhance the support for batch processing, also support for other cluster managers, and also support for Python, because Python is a language that many people know, and it has a rich library, and it is good to be able to run that inside an Apex topology. So there are some resources here if you want to learn more about Apex, or are interested to contribute maybe. And that was it. So I think we have a few minutes for questions. Yes?
What do you mean by integration with Mesos?
Integration with Mesos means that it would run on a Mesos cluster. So right now it runs on Yarn. So Apex is a framework that needs a cluster to run on. It will ask a resource manager for compute resources and for memory resources, and then deploy itself into processes. So that's what it does on Yarn, right? On a just high level. On Mesos, similar, right? There would need to be a framework for Apex, and so that it can run there. Any other question? Okay, great. Thank you for joining the talk, and have a nice day.